Hello folks, this is a quick problem on single variable optimization, and this is going to be the classic hiker problem. So this is a person travels one direction for a little while, turns, goes a different direction, and their speeds change. So let's read the problem. A hiker starting at a point P on a straight road walks east towards point Q, which is on the road and 3 kilometers from point P. So looking down here, here's point P, here's point Q, east of P, and it's 3 kilometers away. 2 kilometers due north of Q is a cabin. The hiker will walk down the road for a while at a pace of 8 kilometers per hour. At some point Z, indicated here on my picture by my red dot, between P and Q, the hiker leaves the road and makes a straight line towards the cabin through the woods, hiking at a pace of 3 kilometers per hour. In order to minimize the time to go from P to Z to the cabin, where should the hiker turn in the forest? So, the steps we're going to follow are draw a picture. Well, we have our picture here. I was nice enough to give that to you. But if I didn't give that to you, you would have to reason through this problem and actually draw the picture. Then we need to define some variables, write an equation, and then the optimization stuff comes in. And critical points, derivatives, things like this. Pardon me. So first things first, let's define some variables and try and determine what we're actually going to be finding. Well, the funny thing about this problem is that the point Z here could be anywhere along this curve. It could be at P, it could be at Q, but likely it is somewhere in between. I drew it just randomly at a point in between. So what we really need to know is where to put Z. And so that actually tells us what our first variable is. Right? We've got this divided into two nice sections, not necessarily equal. I'm going to call one of those sections X, and the other section will be 3 minus X. Now what this actually gives us is all the information we could possibly need for the person's route. For example, that path right there, by Pythagorean theorem, I know that x squared plus 2 squared is equal to that hypotenuse squared. And so that hypotenuse itself is square root of 4 plus x squared. Well, this actually tells us quite a bit of information about how we want to set up our problem. So we've defined a variable. We really need to write an equation now, but the question is, what equation? Well, if you look at the problem, we want to minimize time. So we need an equation for time as a function of x. So what we want is time equals some function of x, and we have to rely on any basic physics, geometry, or anything else like that that we may know in order to get this. So what we actually use in this case is distance equals rate times time. So we're just going to write this as d equals rt. And I know in our case, time is what we're interested in, so time is equal to distance over rate. And we have rates for all of these different pieces. So if we look across the bottom, the time across the bottom of the triangle, so this time as a function of x, will be 3 minus x over 8, because I know I'm going 8 kilometers per hour across the bottom here. So we'll call that time 1. Time 2, that'll be across my hypotenuse side, is going to be 4 plus x squared and then square rooted over 3, because I know I'm going 3 kilometers per hour along that side. So putting all of this together, we can get a function for our time. So let's write it down. So time as a function of x is 3 minus x over 8 plus square root of 4 plus x squared over 3. And now at this point, we're interested in doing the optimization part. So we actually need the derivative. So I need t prime of x. I need to set it equal to 0 and solve. Now this could potentially take quite a bit of algebra. So since the purpose of this video is simply just to show you the steps for the optimization, I'm going to skip the algebra part. This could take you several lines of algebra on your paper, and I'm going to jump straight to the solution here. So once you actually solve this equation, t prime of x equals 0, we're going to get x is 6 over the square root of 55, which is approximately 0.81. So what that means is that on our picture, let's redraw our picture here. On our picture, we had something akin to this, where we turned here, we went this way, this was x, this is 0.81 kilometers, right? So this is 3 minus x, so that would be 2.19 kilometers. And of course we could figure out how long you travel across the hypotenuse as well. Well, it turns out that this is our only critical point that we actually find in this solution, and it seems fairly reasonable that this would be a minimum, but in order to check that it was a minimum, you should then go through the second derivative and make sure that the function is actually concave up at that point. This concludes our example of a single variable optimization problem. The variants of these problems are very, very wide. You can do lots of different things with single variable optimization, but the steps are all still basically the same. I wish you luck, and that's it.